Hello everyone, and welcome back to a continued conversation in Chapter 6. In the previous two conversations, we introduced an application of the integral looking at the computation of volumes of surfaces generated via revolution. In this section, we're going to change the conversation a little bit, although we'll see at the very end, we'll circle back to that surfaces by revolution thing. And for now, instead of looking at a computation of area, here we're going to see if we can't tweak the integral a little bit in order to understand a lower dimensional analog to area, namely length. So you can think of this geometry as the difference between area and, say, circumference of a polygon or something like that. In order for this conversation to work, we do need to use what's called a smooth function, which is a phrasing I used back in Chapter 9 to refer to, say, a smooth interpolant. And again, here, all smooth means is that it's everywhere differentiable. Technically, it means it's infinitely differentiable. And for our purposes, that means no breaks, no cusps, no corners, things of that nature. Now, really, all that means is that it's your standard picture that your calculus teachers have been using forever. This is going to be some sort of a function where I have here some sort of a coordinate system, and I have a function that just goes, say, something like that. This is your standard run-of-the-mill example of a smooth function. Let's call it f. What I'm interested in trying to understand in this conversation is arc length. This is the length of this function. This is, if I were to map this out using string, how much string would I need to have? If this were measuring out some sort of a road or a bridge, you might be interested in how much mileage is it in order to get from point A to point B along this route. It's all sorts of interpretations. Well, in order for us to develop a formula that computes the arc length of a given function, and here we're going to specify we're on some closed interval AB. So we're going to start here at A and end here at B. This is just to make sure that our integration, which we'll discover is the necessary tool, works properly. The way that we build out an understanding of arc length is to be inspired by Riemann sums. The notion of Riemann sums for computing area involved taking your interval A to B, partitioning it into finitely many subintervals, and then using rectangles to approximate the area under the curve. And then what we observe is that if I take infinitely many rectangles and let the partition involve infinitely thin delta x's, then I end up having my approximation become the exact area under the curve in the limit. Here we'll do the same thing. I'm going to come in here and I'm going to take my AB and I'm going to partition it. So over here maybe we'll call this x0 A, call B x, say, n, and we're going to partition everything in between. So maybe this is x1, this is x2, this is x3, this is x4, etc. We'll keep doing that. Maybe at some point in the middle we end up with something like, we'll call it xk, for example. And then, before that, of course, would be xk minus 1. After that would be something like xk plus 1. And this would continue until, say, we hit, let's do xn minus 1. So k is the index we're reserving for an arbitrary point anywhere between x0 and xn. But instead of building Riemann's rectangles that we're going to build here, because we're interested in arc length, instead we're going to pass to what we're going to refer to as the nth, and I'm going to write the word and then pronounce it. This is a polygonalization. Essentially, this is saying, you see that partition we built here? Look at the associated outputs of that partition. So here we have the 0th, 1st, 2nd, 3rd, 4th, These are all the outputs for the partition endpoints. K minus 1, K, K plus 1, N minus 1, and N. And if I want to try to compute the length of the blue curve, instead, as an approximation, I'm going to consider the nth polygonalization, where n denotes how refined our partition is here. And all that's going to amount to doing is taking the connect the dots version of our function. So here we are, we'll connect the dots in some controlled way. There you have it. And of course, that's dot, dot, dot in between these points. Now, of course, you can see just based on the way I drew it, if I figure out the length of the polygonalization, the orange piecewise linear graph, that's not going to be equal to the length of the blue curve. It seems to be, say, an under approximation here, under approximation, sometimes it's an over approximation, and so on. But in the spirit of Riemann sums, if I do figure out the length of the orange polygonalization, maybe as I take a limit as n goes to infinity, this polygonalization will end up getting very, very, very close, and eventually in the limit becoming the blue curve. So now that we've translated the question into how do I compute the length of the polygonalization, well, what we're going to do is we're going to zero in on one maybe specific part of it, because each of these lines look a little different, so let's zero in on one in particular. Well, K here was taken to be an arbitrary point in my partition, so let's look at one special part of the polygonalization, maybe right here around K. So what I'm going to do is I'm going to zero in on this part of the graph right there. The K to K plus 1th part of my partition. Let's zoom in on that real quick. And so down here, I'm going to draw a picture of just that highlighted bit. So if I zoom in on that, this is the picture that I have in mind. I have the blue curve, which looked a little concave up. I have the polygonalization that starts in the upper left, ends in the bottom right, and I seem to be connecting this with a straight line, right? That's the highlighted bit up there. Okay, what are we working with here? Well, let's see. This left endpoint right here has an input of xk, and so an output of, I guess, f of xk. So technically, that's what this point is right here. This point is the point xk, f of xk, whereas this point right here is xk plus 1 to f of xk plus 1. But for the purposes of this polygonalization, and so I don't have to keep rewriting f of xk and f of xk plus 1, we're going to adopt this identification right here. For f of xi, we're going to call that capital P sub I, just so I can make this a little bit easier to talk about. And so that means with respect to this picture down here, this point right here is now xk pk, and this point down here is xk plus 1 pk plus 1. And what I want to do is I want to compute the length of this orange line right here. But if I want to talk about that orange line, maybe I'll give it a name. Let's say that the length of that line, the length of this, we're going to call capital LK, because this is the kth part of my partition. What I see here is, though this is a straight line, I know how to compute the length of a straight line that has a distance formula using this coordinate and this coordinate. But I'm going to be a little specific about how I write it. Remember how the distance formula comes to be. The distance formula comes into existence by looking at the left endpoint and the right endpoint and imagining that the left endpoint and the right endpoint both live on a triangle, specifically a right triangle, where the length of that triangle down here is typically what you would have called, say, delta xk, right? This is what you would have called your xk plus 1 minus your xk. And your height is what you might have called delta pk, where, again, that's going to be your pk plus 1 minus your pk. Well, when you look at this, and I want to be clear here, right? You can see here your pk is going to be taller than your pk plus 1. Well, that's okay. That means if I take the small number minus the big number, that means, you might be concerned, maybe that's going to be a negative number. Yeah, that's fine. It probably will be negative. It won't matter. You can role reverse this if you feel like it. If you want your delta pk to always be positive, that's okay. Because when I turn around and I compute this length here, that's using the Pythagorean theorem. That's going to be the square root of, in this case, it's going to be delta xk squared plus delta pk squared, all square rooted. And so here, whether you want your delta pk to be positive, negative, either way I'm squaring it, so it really doesn't matter. And so this is my length, lk. But this doesn't seem super useful. Sure, I can do this for every one of these little points in my polygonalization, but eventually I want to add them all up and then take a limit, and this just seems kind of complicated to add up a bunch of these and then take a limit. Well, what I need to be able to do is somehow take this formula and simplify it a lot. And fortunately, there is a way to do that. If you're following along with some of the written text that I have here, this is the step that we're at right now. I've justified that lk can be written as this square root. So what that means, reiterating this, is if I were to do this for all of these different junctures and add them all up, I would get a sum of the n lk's, which is the sum of the n, well, this formula, whatever that is. And again, this formula just doesn't feel very easy to work with. I don't really know what this is equal to. This is a little unclear. Eventually, I want to take a limit as n goes to infinity and turn this into an integral. But in order to do that, there should be some sort of a delta xk that turns into a dx. But I can't do that if there's only a delta xk here and it's not applied everywhere. It's not like a common factor. So somehow I need to take this delta pk and reinterpret it as something involving the delta xk, so that I can factor out the delta xk and it turns into a dx. Fortunately, there's a magic tool from Calc 1 that does exactly that. That magic tool has a name. That magic tool is called the mean value theorem. And I can justify it for you right here. Even if you don't remember what that theorem says, look at this picture. Observe this orange line right here. This orange line, well, if I were to take it and I were to move it right there, notice it just went from being a secant line to a tangent line. So in fact, every time I have a secant line, there exists some point, in this case right there, for which my secant line becomes a tangent line. And maybe for the purposes of this demonstration, I'll make that this pink line right here. So the important observation is that the pink line and the orange line have the same slope. And maybe this tangent line is occurring very specifically at some x value. We're going to call that ck. So the observation I want to make right here is that the tangent line at x equal to ck has the slope of what? According to calculus, it should be the derivative at ck. But by construction, the slope of that pink line is the same as the slope of this orange line. Okay, now I'm talking about the orange line, so I'll switch to orange. So what I'm observing over here is that the slope of the pink line, f prime of ck, is the same as the slope of the orange line. Well, by algebra, the slope of a line is just rise over run. Rise of delta pk, run of delta xk. So that should be equal to delta pk over delta xk. The fact that such a ck exists, how we found it over here, that's what the mean value theorem says should exist. So if you didn't know what the mean value theorem is, all you have to do is believe me that this ck can be found by dragging the orange line to become the pink line. That's it. Now, this equality gives us a lot of mileage. What that means is that delta pk, by clearing the denominator, is the derivative at some specific point ck times delta xk. So what I'm going to do is I'm going to use this formula, but wherever I see delta pk, I'm going to swap it for this formulation over here on the right. And when I do that, my summation formula here changes, and we get the following. So here is written in text the fact that delta pk can be written as this by the mean value theorem. And here's what I can say. This value, the length of the polygonalization, the sum of the individual LKs, the lines, we know is equal to the sum of, this is the square root we get from the distance formula. I'm going to swap that delta pk out for its new formulation right here, and when we do that, I get this. Now this is delta xk, and they're both squared. So I can factor this delta xk squared out as a common factor, and then it gets square rooted. So I'm left with the sum of this square root 1 plus f prime of ck squared. And technically, if you really want to, you can put brackets around the derivative there to note that the square occurs at the end. And now the delta xk is sitting outside on its own. This is important because the delta xk right here is what will eventually turn into our dx. So indeed, once I take a limit as n goes to infinity, this quote-unquote Riemann sum becomes this formula right here. The summation becomes an integration. The integrand now comes from that root 1 plus f prime x squared, and the delta xk becomes a dx. This is using Newtonian notation. I could have used Leibniz notation, dy dx, but if I zoom out, this becomes our definition. If f prime is continuous, meaning I can integrate it, then the length, I'll call it arc length, of the curve from A to B is this formula. Now, that was a lot of information. It genuinely was. But I think that it's powerful that we can take the Riemann sum sort of argument and we can tweak it to mean not computation of rectangles, but computation of lengths. And the same premise goes through. For the purposes of this class, I'm going to say it is okay if you merely remember this formula. You will never be asked to reproduce this formula in any way. I just think that since we have the capacity to do so, it might be illustrative to demonstrate the utility and the power of the Riemann sum. At this point, however, we're going to move toward just doing a bunch of examples so that you can sort of see how this works in action. For example, here, I want to find the length of this curve specifically from 0 to 1. It might look a little quirky, but what you'll come to find out is anytime this curve looks quirky, it's because it's being chosen so that the resulting square rooting and the 1 plussing and the squaring and the integration all work out more or less. Let's take a look. So here, if I want to compute the length here, it's going to be an integral from 0 to 1, that's the a and b, of, using the formula up above, the square root of 1 plus, and we're going to square the derivative. And if I do the derivative here, the 3/2 cancels the 2/3, leaving me with an x to the 1/2, then minus 1, which also disappears. So this is just the square root of x squared. Best case scenario. This just reduces into the integral from 0 to 1 of the square root of 1 plus x. And this is an integral we know how to handle. This is just the integral from 0 to 1 of just 1 plus x to the 1/2. And so here we'll do the reverse power rule, and we'll get 1 plus x to the 3/2 all over 3/2. And since it's a definite integral, we evaluate between 0 and 1, which in this case, if I plug in 1, I'm going to get 2 to the 3/2 over 3/2. And if I plug in 0, I'm going to get 1 to the 3/2 over 3/2. And I can clean this up a little bit. It looks like I'm going to end up getting, if I pull out the 2/3 out front, because that's 1 over 3/2, it looks like here I'm going to end up with square root of 8 minus 1. Now, I would have mentioned this earlier in the Chapter 6 conversations, but remember, this is Chapter 6. When we discuss Chapter 8, using methods like integration by parts, trig sub, trigonometric substitution, partial fraction decomposition, all of that was Chapter 8. So when you're working through problems of arc length here in Chapter 6, or surfaces of revolution, note you can't use the Chapter 8 material. It hasn't, quote-unquote, been introduced yet. So every single integral that is going to be expected of you in this section is going to have to be performed using strictly Calc 1 methods. Here, the reverse power rule is a perfect example. So that's just a gentle reminder as we navigate some of these examples. While we're here, I'll also note, here I computed this arc length, right? For this is a function y equals f of x. Note, just like we saw with surfaces of revolution, if instead I have a function of y, then an analogous formula works for that. Namely, if h prime of y is continuous on some interval cd along the y-axis, then the length of that function, x equals h of y, is just exactly what you'd expect. The only main difference is it's now a dy integral. But for many, many purposes, we will stick to x integrals because we want to focus on the arc length computation, not necessarily where our function is defined in terms of what variable. So this is going to be a stopping point for the first half of this conversation, where we've introduced the theory behind the formula and we've done a simple example. In the associated video here, we'll finish off the conversation on this handout where we're going to dive into a couple of examples and we're going to look at some of the frequently encountered phenomena that we expect to see. Additionally, we'll see how to take this two-dimensional idea of arc length and extend it to 3D, and that's what section 6.4 covers, as instead of looking at arc length, we talk about surface area. But that'll be for the next video.